So in this problem we have a 3-pound collar and there's a rod that is given by this equation. It's a parabolic rod and the angle theta increases steadily with time, and this collar will move along the rod in this direction. And there's some force P acting on the rod, and we're asked to determine that, and we're asked to determine any normal component of force acting normal to this direction P. So we want to find out two forces in this problem. And we want to find those forces when theta is equal to 90 degrees. So let's draw the location at 90 degrees. The location of the rod is somewhere right in here. So I'll draw it, the location of the collar, I'm sorry, is right in here. And there's a force P that acts tangent to the rod at this location, and some force N that acts normal to the rod at this location. So I'm drawing two vectors, 90-degree angle between the two. So let's call these forces P and N. The first thing I do when I see a problem like this is make a table of everything that I know. I know theta is equal to pi over 2, for example, and theta dot, it's given to us as 4 radians per second. And it's telling us that the angular rate, theta double dot, the angular rate is steady, which means the angular acceleration is 0 radians, theta double dot, 0 radians per second squared. And I know the equation for r is 4 over 1 minus cosine theta, and if I plug in a value, I know theta is pi over 2, I come up with r is equal to 4 feet. And if I take the derivative of this, I'll get r dot is equal to negative 4 sine theta divided by 1 minus cosine theta, quantity squared, times theta dot. And when I plug in numbers for r dot, I come up with negative 16 feet per second. And if I take the derivative of r dot, I'll come up with r double dot. And again, being careful with the chain rule, I'll split this into two different terms. And I'll have a theta dot squared and a theta double dot. And theta double dot in this problem is equal to 0. That angular acceleration is 0. And when I plug in numbers for the rest of the parameters, I come up with r double dot is equal to 128 feet per second squared. The next thing I like to do is we can calculate the acceleration based on this information in both the radial direction, so here's the unit normal in the radial direction, plus the magnitude of the acceleration in the transverse direction. Here's a theta times the unit vector in the transverse direction. And I've got two equations for these. AR is equal to r double dot minus r theta dot squared. And when I plug in numbers for those, now that I know those parameters, I have AR is equal to 64 feet per second squared. And I can do the same thing for the transverse acceleration, a theta. That's equal to r theta double dot plus 2 r dot theta dot. And when I plug in numbers for those, I'll come up with a negative 128 feet per second squared. So when theta is 90 degrees, the positive radial direction is going straight up, and the positive theta direction is horizontal. And these two, so here's a positive radial direction and the positive theta direction. And what this is saying, when the radial component of acceleration is positive, there's a positive component to it, but the radial or the transverse acceleration is negative, which means that there's some component in the negative theta direction or to the right. And what we'll see is that the actual acceleration of the collar at this location is something in the direction of the red arrow. So a positive radial component and a negative transverse component. So I've cleaned this up a little bit to put the constants that we know out of the way off to the side. And we're in a point now where we can begin writing the radial and the transverse equations of motion, which are just the sum of the forces in both of those directions. And what I've also drawn is a kinematic diagram at theta equal 90 degrees. It shows both this retarding force P and this normal force N. And this is I've drawn it at theta equals 90 degrees such that the radial component of the radial coordinate is pointing upward, so the direction of increasing r is acting upward, and the direction of increasing theta is acting horizontally or to the left. And this pulling force is acting to the upper right, so in a direction with a value of positive r UR and a negative theta component. And the normal, this normal force again has negative components both in the r and in the theta direction. And we're going to need to figure out, to write these two components, we're going to need to figure out the radial component of P and its transverse component. So it's radial component moving upward and transverse component with the dashed lines. We'll need to do that for both P and the radial component for N and the transverse or theta component for N as well. So let's write the radial equation of motion is the radial component of P minus the radial component of N, and that'll equal m times the radial acceleration, which is something that we already know. And we can also calculate the transverse equation of motion, which is negative p theta minus n theta, and that's equal to the mass times the tangential or the transverse component of acceleration, a theta, which we also know. Ultimately, what we're trying to find are the magnitudes of this pulling force and the normal force. But right now, we only know the two components, the radial and the transverse components of it. And what we don't know, or if we knew an angle, for example, of p relative to UR, we could use some trigonometry to calculate these two different components, but we don't know this angle right away. If I zoom in on this picture, it turns out that there's an equation that will allow us to find an angle between the tangential direction of this collar and the extended, what they call the extended radial line. So we've got an equation that will allow us to find this angle. And that equation is psi is equal to the inverse tangent of r divided by dr d theta. And an inverse tangent can return both positive and negative numbers. And if you get a positive number when you implement this equation, what you're getting is this angle here. It's the angle between the tangential direction and the extended radial line. But if you get a negative number, a negative angle, what you'll come up with, what it means physically now, is this angle over here. And you'll see in this problem we will come up with a negative number. So what we're actually finding is this angle here. Turns out we'll get a negative 45 degrees, but remember that we're referring to this angle here, which will, in this case, will turn out to be 45 degrees. So let's implement this. We've got the tangent, the inverse tangent of r, which in r, for this particular problem, is 4 divided by 1 minus cosine theta. And dr d theta is negative 4 sine theta divided by 1 minus cosine theta squared. And if I simplify that, I'll come up with the inverse tangent of negative 1 minus cosine theta divided by sine theta. And I know theta in this case is pi over 2. And when I plug in pi over 2 for this equation, I'll come up with a value of negative 45 degrees, or negative 0.7854 radians. So according to my kinematic diagram then, this angle will be the absolute value of psi. And that means this angle down here will equal pi over 2 minus the absolute value of psi. So now that we know those angles, let's break the components of motion, the equations of motion, into their component form. So let's look at the radial component of p, for example. I can say p is PR is equal to p times the cosine of this absolute value of psi minus n. If I look at the trigonometry now, I want the radial component of n, so I want this side of the triangle, and that will equal n times the cosine of pi over 2 minus the absolute value of psi. And the sum of these two components will equal MAR, which we know. And I can change this cosine pi over 2 minus the absolute value of psi into sine, the sine of the absolute value of psi, and that just simplifies it a little bit. And I'll do the same thing for the theta component, and I'll have negative p times the sine of the absolute value of psi. So I'm looking at this component, and I can do the same thing for n. So n, the cosine, minus n, the magnitude of the normal force cosine. I'm sorry, we're looking for this length here, so it'll be n times the sine of pi over 2 minus the absolute value of psi. So again, simplifying and changing it into cosine, the absolute value of psi, I've got both the radial and the transverse components. And let's look at our knowns. What we want to find are, we want to find p and n. So we've got two unknowns. And we now know psi, we know the mass, the components of acceleration. So we know all of these values. What we're left with are two equations and two unknowns. And if I take the mass, remember we're working a 3-pound mass collar, so we take 3, we need to get it in terms of slugs, so we'll say 3 divided by 32.17 slugs, and I come up with a value of m of 0.0932 slugs. So I've got two equations and two unknowns. And if I solve both of these, what I'll come up with, a value for p is equal to 12.7 pound force, and a value for n equal to 4.2 pound force. So p and n, both positive values, so they are acting in the directions that we propose. P is, it's pulling on it, it's decelerating the block, the rod, or the collar, and n is acting in this direction. It's causing the collar to accelerate in the direction shown.